Right, okay, so this video is looking at buffers. It's going to focus primarily on calculations. So there'll be a little bit of theory or a little bit of explanation about what a buffer is, but it's going to focus mainly on looking at some example calculation questions. So first thing to say is that what buffers are solutions that resist the changes or change in pH. So it's not that the pH doesn't change, and we'll come to see how we can sort of see that visually shortly, but it's not that it doesn't change, it's just that it only changes by a very small amount, assuming that the amount of acid or alkali that we add is in itself also a small amount. So we can make buffers in a variety of ways. The two sort of standard approaches are if you want to make an acidic buffer, so that's a buffer with a pH where the concentration of hydrogen ions is greater than the concentration of OH minus ions, then we would use a weak acid and its strong base salt. So for example, ethanoic acid and sodium ethanoate. And a basic buffer is the sort of converse of that. So we'd use a weak base and a strong acid salt. So for example, ammonia and ammonium chloride. Now, when we come to do calculations, which is what we're going to do shortly, there are two assumptions that are made. The assumptions that are made are, firstly, that our concentration of the weak acid in the calculation is the initial concentration. So whatever they give us in the question before anything else is added, before the buffer is actually made. And then similarly, and this depends slightly on the type of question, but it's still an assumption to be made, the concentration of the salt is also the initial concentration. So even though when we set up a buffer solution, we will be in effect setting up a new equilibria, we still take the concentration of the acid to be the initial concentration, and we take the concentration of the salt to be the initial concentration. Okay. So let's see if we can sort of appreciate a little bit better this idea that a buffer resists changes in pH. And one way that can help us sort of visualize that is to look at a titration curve. So this is a titration curve for a weak acid and a strong base. So you can see how the pH changes as the volume of alkali is added. One of the sort of distinctive features, or the two distinctive features, I guess, of this titration curve are the fact that we have a steeper gradient and therefore a greater change in the pH at the beginning, or when the alkali is first added, and then we get a very shallow gradient, or a shallower gradient in the sort of middle region, I guess, before we suddenly get a very rapid change where our single drop of our alkali changes the pH quite dramatically. So really, all a buffer is, I guess, and don't take this as a literal portion, but is a region, is a specific point, on our titration curve. So if we imagine that we made a buffer and it had a pH that equated to this, so that's the equivalent sort of concentration of weak acid and salt that we had, then we can see that if we add some alkali, the pH only changes fractionally. It's essentially resisting the change in pH. And if we added some acid, so we'd be going backwards, again the pH hardly changes. So it's a sort of visual or a pictorial representation. So in a sense, what the titration curve is telling us or showing us is showing that buffers do exist. It's not some theoretical concept. We can see it physically there on the titration curve. So essentially, when a buffer is made, we are making a solution in which effectively equates to a point on this curve and a point within this buffer region. Okay, so we're making a solution that exists somewhere on this curve with particular proportions of the concentration of acid and salt. We have a Ka value for that particular acid, and we are essentially reaching a point. Now, there are two ways to make buffers. I know I mentioned just on the previous slide about there being an acidic buffer and so on. But if we think about how even making an acidic buffer, there are essentially two ways. We could take a weak acid and we could add a mass of its salt. So we could take ethanoic acid and put in a particular mass of sodium ethanoate. And what that would do is that would take us precisely from, say, the beginning, so from whatever our weak acid was, and then the moment that we added the mass of salt, we would be then reaching a particular point on the buffer region. So sort of like direct. There's no journey there. It's just we're going straight to that point. The alternative, or the other way of doing it, is again we start with our weak acid and we add a volume or we add a volume of a concentration of alkali, which doesn't take us all the way to neutralization, but which takes us to somewhere along the titration curve, again in the buffer region. So there are two ways to make a buffer in effect. One is to add the salt to the weak acid, and one is to partially neutralize the weak acid. So we're going to look at calculations that involve both of those features. Okay, so we'll start with a question. So this video is mostly about, or primarily about, calculations. So we're going to look at a few different types of calculations, and we will refer back at one point to that titration curve that we just saw. So we've got a buffer solution here made by adding 2.05 grams of sodium ethanoate. So that's our strong base salt. And then we've got a volume and a concentration of ethanoic acid, and we're given Ka, and we have to calculate the pH of this solution. So the first thing to say is we are going to have to work out the number of moles of sodium ethanoate. We've got the mass. They've given us the name, so we have to appreciate what the formula of that would be. So when it's a solid, you have to include the metal ion, because this is an ionic compound. So we got ethanoate ions and sodium ions. So we would use our periodic table to do that, and we would get a MR of 82.0. What else do we have that's going to be important and useful? Well, we have a volume and a concentration of ethanoic acid, so that's going to allow us to work out the moles. And we are also given, we're also given the Ka for ethanoic acid, so we've got that as well. So first things first, I think, is to work out the moles of sodium ethanoate. So the mass is 2.05 grams, the MR is 82.0, so we get moles of 0.025. Okay, we also need to work out, we could work out the concentration because we have a volume. So we're adding this salt, so it's a mass, so it's a solid. We're adding it to 0.5 decimeters cubed, so we're dissolving it in that 0.5 decimeters cubed, so we can work out the concentration. Now when it's dissolved, those ions are now separate from each other, so we can now just think of the ethanoate ions. It's moles per decimeter cubed, so it's 0.025 divided by 0.500, and we get a concentration of 0.05 moles per decimeter cubed. Okay, so the next thing to do is, so we've got a concentration of ethanoic acid, we've got a concentration now of the ethanoate ions, we've got Ka, so we should write our Ka expression. You should always do this, and when you first write it, always put the actual formulae in, because there's invariably, or quite often, there is a mark for this Ka expression. So don't try and rearrange it first. You shouldn't do that anyway, because you're more likely to make a mistake if you just try and go straight to the expression you're finally going to use. So you might get a mark for just getting the basic expression there. We're trying to work out pH, so that means we've got to work out the concentration of hydrogen ions. So we're going to rearrange this expression. so that we have the concentration of hydrogen ions as the subject. So that means we are timesing both sides by the concentration of the weak acid and dividing both sides by the concentration of the salt. We can now insert the values. So we've got Ka, which is 1.74 times 10 to the minus 5. We've got the concentration of the acid, which is 0.01. That's in the yellow. And we've got the concentration of the salt. That's what we worked out, which is 0.05. So we end up getting a concentration of hydrogen ions. Of course, when you're writing these numbers down, keep them in your calculator. And then we can work out the pH. So the pH, to remind ourselves, is minus log the concentration of H plus ions. So we're doing minus log of 3.48 times 10 to the minus 6, which gives us 5.46. Remember, you should, or you must, always write your pH to 2 decimal places. Okay, so that's the first type of calculation. We've added a salt to a weak acid, and in this question we were adding a mass of our salt to the weak acid. So let's look at another type of calculation. Okay, so this time we're given a pH, so we have a final pH for this buffer, so we've got a pH of 4.5. So the first thing that we're likely to do, one of the things that we're likely to do quite early on, is work out what the concentration of hydrogen ions that equates to. We've then dissolved X grams of sodium propanoate, so this time we're going to be working out the mass of the salt that we add to produce that buffer solution. We're given the final volume, it's half a decimeter cubed again, and we're given the concentration of the propanoic acid as well, and we're given Ka for the propanoic acid. So first things first, and think that even if this was a 5 or 6 mark question and you're not sure quite how to get to the end, think about the marks you can definitely get, and you can definitely get marks for turning the pH into a concentration of hydrogen ions. So to do that, remember that concentration of hydrogen ions is 10 to the minus pH, so 10 to the minus 4.50 here, which gives us 3.16 times 10 to the minus 5 moles per decimeter cubed. Again, we should write our Ka expression and do it without sort of messing around with it first. So we do the standard sort of equilibria acid, the Ka expression, sorry. So this time it's propanoate, and we've got that over the propanoic acid. Oops, sorry about that. Now we are trying to find out the mass of sodium propanoate. So in this instance, then we're going to need to have the concentration of sodium propanoate. That's going to have to be the subject of our calculation. So this time, so we want that to be the subject. So we're going to have to divide both sides by concentration of H plus and multiply both sides by the concentration of propanoic acid. Okay, insert the numbers. So our Ka value is 1.35 times 10 to the minus 5. Okay, we're multiplying that by 0.25. Okay, because that's the concentration of the propanoic acid, and we're dividing it by the concentration of the H plus ions, which you'd worked out, which is 3.16 times 10 to the minus 5. And that gives us a concentration of propanoate ions of 0.1068. So I could write that as 0.107. I mean, always sort of write your sort of working out to a minimum of 3 significant figures. Don't go overboard, but keep your numbers in your calculator. So we can now work out the moles of propanoate ions because we have the concentration. So it's concentration times volume. We know the concentration is 0.1068. We know that the volume is half a decimeter cubed. So the number of moles is 0.053. Okay, again, I'm keeping that in my calculator. So therefore, the mass, now we are adding sodium propanoate, so we mustn't forget the metal ion when it comes to, this calculation. So when you do your MR, you need to make sure you've included the sodium. So we have now got 0.053, or the number in my calculator, times 96.0, that's the MR, and that gives us a mass of 5.13 grams. So this is almost like a backward version, a reverse version of the previous question we looked at. Okay, let's move on to the next one. All right, now this time, this is a partial neutralization question. So we've got our ethanoic acid, and we are adding potassium hydroxide to it. So we're given a volume and concentration of both. So what we should do to begin with is work out the moles of each of those. So the moles of the ethanoic acid. So we know that the volume, so it's 25 centimeters cubed times a concentration of 0.410. So that equals 0.01025. We're adding sodium hydroxide, but really what we're interested in here is the hydroxide ions. It's a 1-to-1 ratio, so it's the same as the moles of sodium hydroxide. We're adding 10 centimeters cubed. We've got a concentration of 0.100, so we get 1.00 times 10 to the minus 3. Okay. Now, what we've got here is a neutralization reaction. So we are reacting our ethanoic acid plus hydroxide, and when they react, we're going to be making ethanoate ions and water. And what we've got here is we know how many moles we had to start with, and that is going to allow us to work out how much each of them changes by, and then that's going to allow us to work out how many moles there are after the reaction's taken place. So in the before bit, we simply put the moles that we've worked out. So we know that we have 0.01025 moles of ethanoic acid. We know that we have 1.00 times 10 to the minus 3 of hydroxide. At the beginning, before we've mixed them, so this is about using the concentrations, the initial concentrations and so on. The assumption is that we have 0 salt. The water doesn't really matter, but obviously we'll just include that to begin with. So when we look at the molar ratios in the equation, it's 1-to-1. So for every 1 ethanoic acid, it's 1 hydroxide. So if we look at the two values, we can see that the hydroxide is a limiting reagent. So all of that is going to be used up. So we're going to end up with 0. That means we're going to use up that number of moles of our ethanoic acid. So we subtract that. And that is how much salt we're going to make, because this is all a 1-to-1 ratio. So if we've used up this many moles, then we're going to make that many moles, 1-to-1 ratio of the ethanoate ions. So 1.00 times 10 to the minus 3 plus, so that gives us a final 10 to the minus 3. And I'm not going to bother doing the water, but it would be the same. Okay, so next thing is we've now got our moles of ethanoic acid in a buffer and our moles of salt in our buffer. So we move on to our Ka expression. So again, write it out correctly just in case. I mean, with the actual formula in, you can always, simplify it later if you wish. But to begin with, just to be safe, we're trying to work out a pH. So we're going to make that concentration of hydrogen ions the subject. The rearrangement of this I've already talked about in a previous question in this video, so I'm just going to go ahead and do it. Whoops. Okay, now thinking about our numbers, we know that our moles are going to come and feature in here. Now, just before we do that, the first thing to say is when you're looking at this, we haven't actually got the concentration at the moment. Okay, now we have got a total volume. We could work out that the total volume was 35 centimeters cubed. So we could be doing our our moles over volume, moles over volume. But the thing to notice is those volumes are going to be exactly the same, so they cancel out, or they will cancel out. So what I can do here is go straight to using moles. So in this instance, you should always double check, but I've got two concentrations on the right hand side. Both of them I have to work out, but both of them have the same volume. So those volumes would cancel out. And so I can go straight to using moles. So I'm just going to make a note of that. So volumes cancel out. Just so you appreciate that. So you're not wondering why I've just used the moles values in the next part here. So I know Ka is 1.74 times 10 to the minus 5. I can now use moles because the volumes would cancel out. So I've got the weak acid on the top. Okay, and then I've got the salt on the bottom. So they've come from this part of the working out I did earlier. Plug those numbers in. I get a concentration of hydrogen ions. I can then work out the pH using the minus log of that, and I get 3.72. So what was fundamentally different here when you've got a partial neutralization is you have to work out what the change in moles is compared to what you started with. Okay, all right, moving on to the next one. So this is a similar question. We've got our weak acid of 3-chloropropanoic acid. We're reacting it with sodium hydroxide. The one difference here is that we're given a pKa instead of a Ka value. So actually, before I even proceed any further, I'm going to just work out what that is. So Ka is 10 to the minus pKa. It's just like pH. Just like the relationship, between concentration of hydrogen ions and pH. So therefore it's 10 to the minus 3.98, which means our Ka value is 1.047 times 10 to the minus 4. So we've got our Ka already for the rest of the reaction. And from this point onwards, it's exactly the same as the previous question. So first things first, even if you're really not sure how to finish the question, you're given a volume, you're given a concentration, so work out moles. So we can work out the moles of 3-chloropropanoic acid. So we were given a volume of 40 centimeters cubed. given a concentration of 0.200, so we can work out the moles. Okay. Equally, do the same for the sodium hydroxide. What we're really working out is the moles of hydroxide ion, or that's what we're that's what we're really interested in. Given a volume of 15 centimeters cubed, concentration of 0.250, and we get a moles of 3.75 times 10 to the minus 3. And then we do just what we did before. We've got a partial neutralization. We can see that the limiting reagent is the sodium hydroxide. We have fewer moles of the hydroxide ions than we have of the weak acid, so it's a limiting reagent. So we write the reaction equation out like we did before. So there's our weak acid reacting with OH minus ions to produce our salt. Oops, sorry, let's just make that a bit clearer. Plus water. We're going to have the moles before. We're going to have the change in moles. And we're going to have the moles after. We've already worked out the before because that's how we started the question. So of the weak acid, we have 8.00 times 10 to the minus 3. The hydroxide ions, we have 3.75 times 10 to the minus 3. We haven't reacted any of the weak acid yet, so we make the assumption that the salt is 0. And then as the hydroxide is the limiting reagent and we have a 1-to-1 ratio, that means all of the hydroxide is going to get used up. So that ends up being 0. We take away that number of moles from the weak acid. And we make that number of moles of the salt. So the same as the previous question. Now I'm just, for the sake of the rest of this calculation, because that 3-chloropropanoic acid is a bit of a hassle to write out, I am going to use a simplified version of the expression. I wouldn't do this in an exam. Well, I would do the correct expression to begin with, and then if you want to switch, that's fine. Sometimes in the exams they call it HA or HX. You should use whatever they give you. So I want to rearrange that. I'm trying to work out the pH. So I want the concentration of hydrogen ions. That's my subject. I'm going to multiply both sides by the concentration of the weak acid, divide both sides by the concentration of the salt. I'm going to insert the numbers. I worked out what Ka was earlier in the question. So that is 1.047 times 10 to the minus 3. I mean, I could work it, 10 to the minus 4. I could work it out again there and have the whole number. I'm multiplying it by the moles, because remember the volumes will cancel out. That's something we stated on the previous question. So here the volumes will cancel out. So I can use the moles of the weak acid and the moles of the salt. Gives me a concentration of hydrogen ions of 1.187 times 10 to the minus 4. And then I can work out the pH because it's the minus log of that. So I get 3.93. Great. Right. So what have we got here? Right, so actually I've got the first part of it is the same as the previous question. So it's the same buffer that's being made. And then now the change is, or the thing that's happening post the previous question, is that we're adding a small volume of hydrochloric acid, and we have to calculate the pH of the buffer after this solution. So we've already worked out the first part, right? We've already got to this bit here. And now we're adding the hydrochloric acid. Now, understanding what's happening here is going to be crucial to helping you especially in an exam, work out what it is that you need to do. So what we're going to do is we're going to look again at our titration curve. So essentially, this buffer that we've made is this spot here. Then we'll just take it to be that spot there. Now, when there are often questions where they either add an acid or an alkali to a buffer, and then you have to calculate the new pH. So you have to decide, are you going along in that direction of the titration curve, or are you going along, say, to the left? Which direction it is going to help you understand whether you're making more salt and whether you've got more salt and less acid, or whether you've got more acid and less salt. So in effect, if we are adding hydroxide ions, then clearly we would be going to the right, because that's like, look, volume of alkali added. So that's our adding hydroxide ions. If we did that, then we would have less of the weak acid. So we would have fewer or less H+ ions, and we would have more of the salt. So what that means is when we work out how many moles of the hydroxide we've added, then we're going to add that number of moles to the moles that we started with the salt, and we're going to reduce the number of moles of the weak acid by that amount. Conversely, I hope that made sense. But anyway, conversely, if we added some acid, we would clearly be going towards the left of this titration curve. So we're adding H+ ions, so we're adding, in this case, HCl. If we do that, then we're going to get more H+ ions, and we're going to get less or fewer A- or salt ions. The point is we're shifting the equilibrium. Okay, that's essentially what we're doing. So we're either moving to the right or we're moving to the left here. We're either, so that is, we have to decide which it is we're doing, and then that's going to tell us which of the salt and the acid we're adding moles to and which of them we're taking moles away from. So in this particular question, they are telling us they are adding 5 centimeters cubed of hydrochloric acid. So we are adding more H+ ions. If we are adding more H+ ions, then we are going to make more of the weak acid, and we are going to have less of the salt. Okay, so that's going to help us now with this particular calculation. So let's do it. So I've already written the Ka value. I'm not going to work that out again. You saw it earlier. I've also already written the moles that we worked out from the original information. So we're going to take it from here. If this was a whole question from scratch, you would have to have obviously done those things already yourself. But as we did it in an earlier version of this question, sort of going to start at this point. So the next thing we need to do is, we've got our moles of propanoic acid in our buffer. We've got our moles of chloropropanoate in our buffer. So sorry, just to be absolutely clear, so this is in the buffer solution at the start. Okay. So it is what we worked out earlier. Now we are adding hydrochloric acid. So, and we're given a volume and we're given a concentration. Be careful, sometimes you're given moles, so always read the information carefully. If you're given moles, that means they've already done this calculation for you. But we're adding moles of HCl, we need to work that out. We're adding 5 centimeters cubed with a concentration of 0.0400. So the moles of HCl or H+ ions is 2.00 times 10 to the minus 4. So we're adding that amount of H+ ions. That means we are going to increase our weak acid by that amount, and we are going to decrease our salt by that amount. So we are now going to work out the new moles. So this is post adding the HCl of our weak acid. So 3-chloro-propanoic acid. So we've got our 4.25 that we started with times 10 to the minus 3. We're increasing it by 2.00 times 10 to the minus 4. Let's zoom in a little bit. So that gives us a new moles of 4.45 times 10 to the minus 3. We also now have a new moles of the salt. So we started with 3.75 times 10 to the minus 3. We are reducing it by 2.00 times 10 to the minus 4. That's the moles of the HCl. So we get 3.55 times 10 to the minus 3. And now we just simply do the calculation as we would normally do it. So I will go straight to the concentration of H plus ions equals Ka concentration of the weak acid over the concentration of the salt. Plug in the numbers. We know that Ka is 1.047 times 10 to the minus 4. And we know that the concentration of the weak acid now is 4.45. So this is post adding the hydrogen ions or the HCl. We've got our new, sorry, did I say concentration? That's actually the moles, sorry, of course, because the volumes cancel out. And now we've got the new moles of the salt. Gives us a concentration of hydrogen ions. We can use that to work out the pH, so minus log of that. Is 3.90. So we added 5 centimeters cubed of HCl, and our pH has changed by 0.03. So you can see how it has changed. The pH has decreased, which we would expect by adding an acid, but that change is very small. So that's how we can describe it as resisting the change in pH. So I hope going through those example calculations has been useful. In pretty much every AQA exam, there's been a 5 or 6 mark buffers question. But I think also these calculations help you appreciate or help you understand some of the other calculations that you have to do in the acids and bases topic. So I hope that was helpful, and I look forward to hearing your thoughts on it.